So in our previous video, we kind of discussed kind of the steps we're going to take or the big picture idea of how we're going to derive a formula to give us the arc length of a curve in class. We're going to use the distance formula, the idea of kind of Riemann sum-like things, and then use this idea of taking the limit as the number of little line segments goes towards infinity. We'll get all of that information together in class. But what I want to do here is, well, is just give us a little bit of a spoiler and tell us what the arc length formula is, and then apply that to a problem together. So as we'll see in class through our derivation together, the arc length formula for a function that's y is a function of x. So let's just say that y in this case is a function of x. We'll see in general, we could have the opposite case, x is a function of y. We'll get there together, is the following. The length of that curve between 2 points, say x equals a to x equals b, some starting and ending x values, of the integral 1 plus the derivative of our function, dy dx, squaring that derivative, and taking that integral with respect to x. So that is our spoiler formula that we're going to derive together. And again, we're going to derive this in a very generalized way, but let's actually apply this formula to a problem, just to get a little bit of practice with this formula. So let's consider the following curve. We have our coordinate plane, y and x, and this will be a curve, let's say, something like the curve. This isn't a line, but this is equal to, let's say, 2 times x to the 3 halves. And actually, just because we already used a lot of 2's, let's get rid of that 2 coefficient, and let's make that coefficient something like 7. And let's compute the arc length between, say, 1/2, and let's say x equals 13. Curve not drawn to scale, for that matter. So we're interested in computing that length. So let's think about what we need for our arc length formula. So up above, a few things we need. We need a top bound, we need a lower bound for our integral, and well, very conveniently, we have those starting and ending points there for us, just points that I'm giving us in the problem. And the last thing we really need for our arc length formula is, well, we need to compute the derivative of our function, and then put that derivative of our function under that square root after squaring it. So our function in this case was y is equal to 7x to the 3 halves. So if we compute the derivative dy dx, we get to use the differentiation power rule, where we bring down that power in front, so bring down that 3 halves, and then deduct 1 off of that 3 halves in that power. So subtracting 1 off that 3 halves. So our derivative in this case is equal to 21 over 2 times x to the 1/2. So now that we have that derivative, we can go back and plug that derivative into our formula. So let's start plugging some stuff in. We have our formula for arc length is the lower bound, which in this case we said was 1/2. The upper bound, which we said was 13. We take the square root of 1 plus the derivative that we found, and we square that. So we have 21 over 2 times x to the 1/2. dx. And that's just plugging in all the information for this arc length formula. So at the name of the game now, we have that integral, it is set up. We get to go ahead and try to compute that integral. So our integral is from 1/2 to 13. We have the square root of 1 plus, well, We have 21 squared all over 4 times x to the 1/2 squared. That just gives us an x to the first power. So remember, when we have x's to powers, we multiply those powers. So this is really x to the 1/2 times 2, or we just get x to the first. So we have this square root looking integral, but for us, if we stare at this for a few seconds, this is actually a u substitution problem, since we see the power of x is a first, so we don't get to jump into trig sub, unfortunately, in this example. So if we let u equal 1 plus 21 squared over 4 times x, well, du in this case is going to be equal to 21 squared over 4. Our du dx is 21 squared over 4. And then if we solve for dx in terms of du, we will get dx is equal to du all over, well, 21 squared over 4. So let's plug all this stuff into the integral. So our integration bounds, remember though, are with respect to x. So we have x equals 1/2 to x equals 13. So they are not with respect to u. Then we now have the square root of u. And after we change our dx into du, we now have du all over 21 squared over 4. So remember, whenever I have square roots, I like rewriting them in integrals when possible, when it's just a variable square root like this, as the variable to some power, in this case, the 1/2. So I'm going to bring that other 4 over 21 squared out in front. Remember, when we divide by a fraction, we reciprocate and multiply. And then we have our bound still, x is equal to 1/2, x is equal to 13 of u to the 1/2 du. And now we're at the stage where we can use the antiderivative power rule to help us compute that antiderivative. So taking the antiderivative power rule, we have 1/2 plus 1, or u to the 1/2 plus 1, and we divide by that 1/2 plus 1 as well. And at the end of the day, we want to evaluate this at x equals 1/2 and x equals 13. Again, I'm emphasizing here that these integration bounds are with respect to x and not u. All right, so our antiderivative is u to the 3/2 all over 3/2. And again, we're going to evaluate this at x equals 1/2 and x equals 13. So I'll just, again, we're dividing by a fraction, so I'll reciprocate and multiply. So that'll be 4 over 21 squared times 2 over 3. So that'll give us 8 over whatever 3 times 21 squared is. And then we have that u to the 3/2, and well, I'm just going to replace that u to the 3/2 with what we called u previously, which was that quantity 1 plus 21 squared over 4 times x. And finally, our antiderivative is in terms of the original variable, which is x, so we can plug in those integration bounds. So let's go ahead and do that next. Oops, I forgot that this quantity 1 plus 21 squared over 4x is raised to the 3/2. So please remember to put that in there. All right, so that coefficient out in front will multiply both of these terms. So plugging in the top bound first, we have 1 plus 21 squared over 4, all times 13. And again, this thing is being raised to the 3/2 minus, plugging in the lower bound, 1 plus 21 squared over 4, evaluated at 1/2. And again, we raise that to the 3/2 power. And that is the length of the curve for this particular example. And again, if we had our calculators handy, we could probably get a very nice value for this. But again, this is what that length is exactly.